Good afternoon. Today it's my pleasure to introduce Professor Roger Howe. Roger received his PhD from the University of California, Berkeley in 1969. I guess that means his PhD diploma has the signature of Ronald Reagan on it. Roger became a full professor at Yale University at the tender age of 29. In 2002, he was honored as the William R. Kenan Jr. Professor of Mathematics, and he retired last year, 2016. Roger's mathematical research investigates symmetry and its applications. He is well known for his contributions to representation theory, and in particular, the notion of a reductive dual pair, also sometimes known as a Howe pair. He was elected a Fellow of the American Academy of Arts and Sciences and a member of the U.S. National Academy of Sciences. In 2006, he was awarded the American Mathematical Society Award for Distinguished Public Service in recognition of, quote, multifaceted contributions to mathematics and to mathematics education. He has been a HKUST IAS visiting member since 2011. As a finishing graduate student at the University of Chicago, I met Roger in October 1981. So we have known each other for slightly more than 35 years. He was my postdoctoral mentor at Yale. Yesterday over lunch, Roger and I had a wistful conversation about being older. Looking back over 35 years, the focused area of mathematics, which Roger and I share, has undergone major achievements, and it can surely be said the entire subject of mathematics has witnessed astonishing achievements these past 35 years. Mathematics and astronomy are arguably the two oldest sciences, but also sciences with wide open outlooks. I'll say that both mentally and physically. Mentally for mathematics and physically for astronomy. Okay, so I see Roger has changed the title of his talk. So today he will speak to us on uncertainty and representation theory. Thank you, Roger.
Thank you very much, Alan. Yeah, so actually I wanted to call this talk 90 Years of Uncertainty. So Werner Heisenberg formulated the uncertainty principle in 1927. So that means 90 years ago. And so roughly speaking, so it was part of the then very rapidly and fresh developments in the field of quantum mechanics. And Heisenberg realized that it was no longer the case that you could assume that you could know all the traditional information about a particle exactly at the same time. In particular, the uncertainty principle stated that the more exactly you know the position of a particle, the less exactly you know its momentum, and vice versa. So this is understood as a consequence of what are known as the canonical commutation relations, which are some of the bedrock of quantum mathematics. And so I'd like to talk about them. It turns out they're also very much at the root of the field of mathematics that I have studied during most of my career, which is representation theory. What was realized that it was realized that quantum mechanics required you to think somewhat differently about what particles were. And particles were no longer little points in space, and particles became vectors in a Hilbert space. And then measurements became operators on that Hilbert space. So the whole framework of quantum mechanics is very much more abstract than classical mechanics. And there's no longer, you don't have little pictures of particles moving around. So for the simplest situation is a single particle moving in one dimension, and then the Hilbert space is just functions on the real numbers. And to be technical, you would say they're square integrable. So if you square them and integrate, you get a finite number. So they're not too big, and they die off at infinity. But basically, it's functions on the real numbers. And then the position operator, so if you want to measure the position of something, what you do, if the particle or the state is represented by a function f, squiggly f there, then what you do is you multiply that function by the coordinate on r. So that's the multiplication operator, or the position operator. And then if you want to find out the momentum of a particle, so this is sort of how fast it's moving, you differentiate the function. So you see, so differentiation is about infinitesimal changes in position. And so the momentum operator, the momentum variable is found by differentiating the function. And physicists multiply by this weird constant, which means something to them. But being a mathematician, I'm going to get rid of that pretty soon. Okay, so you've transferred you look and see where the particle is. You measure it against, you've got little numbers on the number line, and you see where it is. Instead, you multiply it. This function that represents it, you multiply that wherever it is by the value of the coordinate at that point, and then that's your new measured state of the particle. And the key thing about these two operators, the position and momentum operators, is that they don't commute with each other. So that's the basic reason for uncertainty. If they did commute with each other, then you could find out exactly where the particle was. Then you would find an eigenstate for the momentum, for the position operator, and then the momentum operator would preserve that eigenstate if they commuted, and then you could find out the momentum. But they don't commute. Instead, if you look at the commutator, that is the difference of you do the operations in one direction, one order. First you do multiplication, and then you do differentiation, or you do them in the opposite order. Then you get something that's non-zero. You get a multiple, actually, of the identity operator. So this constant, which was in the momentum operator, times the identity operator. And usually people just omit the identity operator from the notation and just write the constant there. Okay, so this is the big new thing. This is the reason for uncertainty, is because these two operators do not commute with one another. And as I said before, I don't really like to deal with that IH over 2 pi, so I'm just going to look instead at the renormalized momentum, which is just differentiation. So you just look at sort of how fast the function, the particle state is changing in each position. I'll call that the unnormalized momentum. So if you do that, then the commutation relations become even simpler. Just the commutator of multiplication and commutator of position and momentum is just the identity operator. Okay, and then, so that was for one particle in one dimension, but usually you want to deal with several particles, and particles actually seem to live in several dimensions, so you may need a lot of variables, which we could call xi. And then for each variable, you'll have a position operator that tells you sort of where in that coordinate direction the particle is tending to be. So that's your position operator, the ith position operator. And similarly, you'll have a partial differentiation in that direction that tells you sort of how the particle is moving in that direction. So that's the momentum operator in that direction. And so I'm going to abbreviate, not put the coordinate things in there, just the indices. So I'll say mi, this is multiplication by the coordinate x sub I, and pi is just differentiation with respect to xi. And then if you take all those operators together, then the ones that involve different coordinates, they commute with other. They don't interact, they commute with other, that's fine. But the ones that involve the same coordinate don't commute. They satisfy the same commutations as the one-dimensional things. So you can summarize that this way, that the commutator of mi and pj is delta ij, where delta ij is Kroneker's delta. It's 0 if they're not equal, it's 1 if they are equal. So that Kroneker's delta times the identity operator. Okay, so that's the canonical commutation relations for many particles living in many dimensions. And so the CCR are often associated with Heisenberg, and in fact, I've always called them the Heisenberg commutation relations. But as I said at the beginning of the talk, Heisenberg didn't formulate his uncertainty principle until 1927, but the canonical commutation relations were actually first stated by Max Born in 1925. So maybe that's a little bit of a misnomer, but it's pretty common terminology these days. And they're intimately related. And the fact that the canonical commutation relations imply a Heisenberg uncertainty principle was first shown in a precise way in a 1927 paper by E.H. Kennard. I thought it would be nice to name somebody who was not totally famous. Okay, so first of all, I mean, the canonical commutation relations were first presented as relations between these specific operators. But as quantum mechanics developed, people became less certain that they wanted to just restrict themselves to those particular operators, and they thought that the canonical commutation relations themselves, not the specific operators, were sort of the most fundamental aspect of this structure. So there was this debate about what we really care about, but this was sort of this debate was sort of cut short by a very important result by Marshall Stone and John von Neumann, who proved independently that what is now known as the Stone-von Neumann theorem, that these particular realizations of the operators, so mi being the multiplication operator by xi, and pi being the differentiation with respect to xi, on some large dimensional space and many functions of many variables, that these are in some sense the only possible realization of the CCR. So the CCR sort of come along with this space built into them. And so there's some caveats here. First, it's very important that these operators, well, if I multiply mi by I by the square root of -1, so this the multiplication operator. The multiplication operator is actually a Hermitian operator. So I'm not going to explain Hermitian. So you have to know what that is. So anyway, this is a Hermitian operator, and this one is a skew Hermitian operator. And so we want to multiply this guy by I to turn this into a skew Hermitian operator. And then these will be both skew Hermitian, and that's extremely important. The reason is that if you exponentiate skew Hermitian operators, you get unitary operators that will preserve the inner product on the Hilbert space you're working with. So, so these are skew Hermitian operators. And there's also a few other small regularity conditions. If you just make those two caveats, then the canonical commutation relations, in fact, uniquely specify those operators, but of course not exactly, right? There's some weaseliness about this, because if I were to conjugate everything by some unitary operator, we get another system of operators which maybe you totally wouldn't recognize, but I could just get back the usual ones by conjugating back. So there's a notion of unitary equivalence, up to some kind of conjugation by unitary operators, something that doesn't change the Hilbert space structure. Okay, so these three conditions, that the operator should be skew Hermitian, there should be a couple other mild regularity conditions, and then we're only dealing with things up to some kind of change of coordinates by unitary operators. Then they're unique. Okay. And this is sort of where representation theory comes in, and I'd like to say that in fact it was quantum mechanics that sort of gave rise to representation theory. I'm going to explain that in a minute, but let me first talk about this particular representation. So it turns out that there's a very lovely way to interpret the Stein-von Neumann theorem in terms of unitary group representations. So yeah, so let me talk about the role they play in quantum mechanics. They enter naturally into quantum mechanics, and in fact were kind of inspired by quantum mechanics. And the reason for that is, so one of the big discoveries of the 20th century was a lot of physics is about symmetry. So if you've got a Hilbert space and you have a symmetry of it, that should mean that you have some linear transformation of the Hilbert space that preserves the inner product on the Hilbert space. In other words, a unitary operator. So if you have a physical system with some symmetries, each symmetry should be realized by some unitary operator. There should be a lowercase g, sorry about that. So for every symmetry, we have an associated unitary operator. And if you have a collection of symmetries, a group of symmetries of the system, then this correspondence between group elements and unitary operators should preserve the group structure, should preserve group multiplication. And this kind of a mapping from group elements to unitary operators is exactly what is meant by a unitary representation. So when you have systems with symmetries, unitary group representations are sort of going to automatically appear in your theory. And so representation theorists have been taking that as license to study all kinds of representations of all kinds of groups. And in fact, in the late 30s, there was really extreme enthusiasm for symmetry, and Eugene Wigner went so far as to say, define a fundamental particle as being an irreducible representation of a certain group, the Poincare group. I won't explain what that group is, but it's related to special relativity. Anyway, for us today, the first point I want to make is that the first unitary representation comes directly out of the canonical commutation relations. And in fact, it was Hermann Weyl who pointed out that the canonical commutation relations are essentially the defining relations of a Lie algebra, which mathematicians these days usually call the Heisenberg Lie algebra. So we've kind of enshrined Heisenberg in the canonical commutation relations. And more precisely, if we take the vector space, the real vector space spanned by the square root of -1 times the position operators and the momentum operators, and also square root of -1 times the identity, this will be a Lie algebra of skew Hermitian operators, meaning that if I take commutator of any two guys, take any linear combination of these guys, take a linear commutator of two of them, it will land back inside that linear span. So it's a Lie algebra. And it can actually be explicitly realized as matrices. And the matrices that look like this. So you take matrices that are 0 almost everywhere. So it's got zeros all in the lower half and almost all in the upper half. Only has non-zero entries along the top row and the last column. And so we'll call these entries X and these entries Y. And so this is the Heisenberg-Lie algebra. And so this may say, wait a minute, I thought you said the only way to realize this Lie algebra was is by means of the multiplications and the differentiations, the canonical commutation relations. Well, what's the secret here? The secret is these matrices are strictly upper triangular, right? They're kind of the opposite of being Hermitian. So when you allow yourself non-Hermitianness, you can stick the Heisenberg-Lie algebra in finite dimensions. But if you require things to be Hermitian, it takes an infinite dimensional space in order to fit it in. And then the associated group can be gotten just by exponentiating those operators, and the exponentials of those operators on the previous slide look like this. The x's and the y's are still the same, and the z is still the same, and then you get 1/2 of the inner product of the x's with the y's as an extra component in this upper right-hand corner. Okay, so this is the Heisenberg group associated with that Lie algebra. Okay, and this group is almost commutative. It's the commutator of any two elements in the group will look like this. You see, this has zeros everywhere except along the diagonal. And then in this extreme upper right corner, it has a non-zero entry. This is the center of this Heisenberg, or the commutator subgroup of this Heisenberg group is just this one-dimensional thing that just has one coordinate up there in the upper right-hand corner. Everything else is 0. So the commutators in this group are very constrained to belong to this one-dimensional subgroup, which in fact is the center of the Heisenberg group, so that if you then take a commutator again, you're just going to get the identity. So twofold commutators inside this group just reduce to the identity, and this group is called, for that reason, two-step nilpotent. So it's almost an abelian group, but not quite. The non-commutativity is essential. That's what gives you the uncertainty principle, but it's sort of the minimal possible kind of non-commutativity. Okay. So then we have then these skew Hermitian operators that realize the canonical commutation relations, and then if you exponentiate them, you're going to get unitary operators, and they will generate a group which will define a unitary representation of this Heisenberg group. So built into the canonical commutation relations are this natural unitary representation of the Heisenberg group. And in some sense, this is a very big representation. It's what's called irreducible, which means that there's nothing like eigenspaces. You can't find any spaces that are invariant under the group. Any vector in the whole space, if you move it around by the group and take linear combinations, you'll get the whole space. So this is very seriously moving the vectors around in this space. And there's no proper subspace that's invariant under the whole group. Okay, so it's irreducible. Of course, the operators, the multiples of square root of -1 times the identity, they exponentiate to these scalars of absolute value 1 times the identity. So just roots of unity or things on the unit circle in the complex plane times the identity. This is what the multiples of the central element do. Okay, so in this language then, we can restate this or reinterpret the Neumann theorem to say that the above representation of the Heisenberg group is the only irreducible representation of H that does the same thing on the center, right? So the center acts in a particular way, and it could act in slightly different ways. We could sort of stretch the center a little bit, and then things would be a little bit different. But if we fix that action on the center, this is the only unitary irreducible representation of this group. And again, we have to use this equivalence relation up to unitary equivalence. Sort of just is the standard equivalence of quantum mechanics. Yeah? Well, I will defer to this, but it acts as a phase change, and strictly speaking, phase changes don't matter in quantum mechanics. So maybe it doesn't do anything, but from the point of view of representation theory, it is that phase change that is resulting, that is making the thing non-commutative and is giving the irreducibility. So mathematically, it's extremely important. I'm not sure exactly the physical interpretation of it. We have a couple of physicists here who maybe can help with that afterwards. So anyway, after the Stone-von Neumann theorem and after the invention of quantum mechanics, representation theory became an intense focus of research in mathematics, and there was a huge amount of progress made. And the most challenging examples, the hardest groups to find the representation of, are what are called the semi-simple or the reductive groups. And these consist of a class of sort of discrete examples, the general linear group or special linear group. These are just the n by n invertible matrices, or the orthogonal group. So these are the isometries of some inner product. And I should say here that the inner product is not necessarily, this may suggest to you a definite inner product, but the inner product may be indefinite. So this ON here is actually sort of a two-parameter family, depending on how many negative positive variables you have and how many negative variables. So like the group of special relativity would be O31. And the normal rotation group in 3 dimensions would be just O3. And then the symplectic groups, which are sort of less well known in the popular imagination, but will play a very important role in this talk. These are the isometries of a skew-symmetric bilinear form, such as the commutator form on the Heisenberg group. So that's why this is relevant here. And then there's, let's say, twisted forms, like so you have the ordinary orthogonal group, or you can consider these forms with pluses in some positive definite directions, some negative definite directions. So these are the main examples. Each one of these is an infinite family. This is one parameter. This is in some sense 2 parameters, and also 1 parameter, but infinite number of examples. And then there's 5 more very, very special cases called the exceptional A groups, which have never gotten names beyond these acronyms. So the main goal of representation theory for a given group is to classify the irreducible representation, the irreducible representations. And in this connection, I have to mention that that mathematicians who've studied the semi-simple groups have found for a lot of good technical reasons, they study a wider class of representations than just the unitary ones. These are called the admissible representations. So they're a nice class of representations that have nice technical properties that include the irreducible unitary ones. And the classification of the admissible representations has been accomplished. And now the main work is to find the unitary representations inside the admissible representations. And there's been a large project devoted to this, known as the Atlas Project, that has made a great deal of progress on this. And some of the members of that project might claim that they're done, but if they are done, it's kind of an indirect way. It's kind of like an oracle. You can take one of these admissible representations of one of the semi-simple groups, and you can feed some data about it into a computer and ask, is it unitary? And the computer will work for a certain amount of time, and if the group is not too big, it will come back with a yes or a no. Okay, so and anyway, this is certainly done for groups up to a certain size, but not in a very transparent way. Okay, so so I've gotten away from the Heisenberg group. The Heisenberg group is an opposite type of group from those semi-simple groups. It's what I call two-step nilpotent, and the nilpotent groups, their representation theory is in some sense very well understood, and in particular the Heisenberg group is understood via the Stone-von Neumann theorem. But it turns out that the Heisenberg group sheds a great deal of light on the representations of the classical groups. And this is sort of what I've worried about for quite a lot of my career, so I'd like to talk about that a little bit. So you might want to think of the Stone-von Neumann theorem as saying some things are very dull. If you have these operators satisfying these relations, then there's only one way to realize them, so it's sort of no choice. But it turns out that this dullness can be used to produce another group representation, and this other group representation turns out to be very interesting. And what is that? So the Heisenberg Lie algebra and its associated group turns out that they're highly symmetrical objects. Okay, the Heisenberg group has a large group of symmetries on it, and that group, in fact, is exactly the symplectic group. So if you take the real linear span of the non-scalar operators in the Heisenberg Lie algebra, so the square root of -1 times the position operators and the momentum operators, if you take the real space, vector space spanned by those, then on that space, the commutator of two of those guys is going to be a multiple of the identity. So that gives you, and the commutator operation is linear in the first factor and linear in the second factor. So you have a bilinear scalar valued pairing on the space W. And it's non-degenerate in the sense that if you have any particular element of the space, any linear combination of these guys, then you can find another one such that the commutator is non-zero. So this skew-symmetric, bilinear, non-degenerate pairing is called a symplectic form. Okay. So, and it turns out that the linear transformation, just like the linear transformations that preserve the ordinary inner product in Euclidean geometry is a fairly large group. Also, this symplectic group that preserves the skew-symmetric forms is a very large group. In fact, in some sense, it's slightly larger than the orthogonal group. But anyway, it's a very rich group. And it acts then as automorphisms, i.e. symmetries of the group structure on the Heisenberg-Lie algebra and on the Heisenberg group. And this, combined with the Stone-von Neumann theorem, this has a very interesting consequence. So you can, you can take the standard representation of the Heisenberg group given by the Stone-von Neumann theorem, and then you can act by this some element of the symplectic group, and it doesn't do anything to the center. So it leaves the center alone. So the Stone-von Neumann theorem says that's really the same representation as you had before. It's unitarily equivalent to the previous representation. So what that means is that there's some unitary operator on your space such that if you conjugate inside the group of unitary operators, that will have the same effect as if you act by the symplectic automorphism on the Heisenberg group. Okay, so you get this equation here that conjugation in the group of unitary operators accomplishes the same thing as acting by that group element on the Heisenberg group before you represent it. Okay, yeah, so this omega g normalizes the image of the Heisenberg group, and when you conjugate it by, you produce the automorphism that was given by G. And this, because the irreducibility implies that this operator is unique up to scalar multiples. So obviously, if I go back to this equation and I say, okay, I want to multiply omega by -1, I change this by -1, this also gets multiplied by -1. The two -1s cancel out, and I'll get exactly the same equation. So this omega can only be determined up to scalar multiples, but that is the extent of its ambiguity. Okay, and now here's a kind of a tricky point, and let me run through it for you. So, like I say, the relation, so the omegas are only defined up to multiples. And so that implies that if first you conjugate by, say, omega g prime, and then you conjugate by omega g, right? Over here, you're going to have gg prime, and over here you're going to have omega g times omega g prime. So that means that you have to have this equation, that the product of omega g and omega g prime is going to have to be omega gg prime, except it's only determined up to multiples, so it'll have to be omega gg prime times some scalar. Okay. So what about those scalars? It's hard to know what they're like. So they're kind of annoying, and anyway, the scalars are called a cocycle, and you kind of like to get rid of them. So you can try to get rid of them. You can multiply each omega g. If you get some complicated bunch of, if you get a complicated cocycle beta g of g prime, you can try to simplify it by multiplying each one of the omega g's by some scalar, and then that will, when you follow through the equation, that will change the cocycle. And you might say, well, is there some way I can choose those scalar multiples in order to completely get rid of the cocycle? Can I make it identically equal to 1? So this is what people like to do. It's called killing the cocycle. And it turns out that the answer is you can almost do it, but not quite. So what happens is that you can make the scalars equal to plus or minus 1. You can't completely get rid of them. So it turns out that you don't get a representation quite of the symplectic group, but of what's called a twofold cover. So for every operator in the symplectic group, you get two operators, which are the negatives of each other. And then they fit together to make a unitary group inside the big unitary group of the Hilbert space. And this twofold cover is, you can't get rid of it. You can't simplify it anymore. And so it's been called, since it sort of involves some kind of square root, anyway, it's been called the metaplectic group. So this is the twofold cover of the symplectic group. And this was first constructed by Irving Siegel and David Shale in connection with the quantum field theory in the early 1960s. And then shortly after that, André Weil gave a more systematic and general discussion. And interesting, the motivations of these two papers were extremely different, okay? Siegel and Shale were worried about quantum field theory. André Weil was worried about number theory. It turns out that this representation is also very closely related to what's called the theory of theta series in the theory of automorphic forms, which is one of the deepest areas of number theory. I call this representation the oscillator representation. In the literature, it's sometimes called the Siegel-Shale-Weil representation, or just the Weil representation. And I call it the oscillator representation in order to not have to decide between these two. And in order to recognize its genesis in physics and its connection with the harmonic oscillator. I'll say a little bit about that in a few more minutes. And also, it's in some sense, it's a strong analog of the spin representation. So the spin representation is related to orthogonal groups. This representation is related to symplectic groups. And there are very strong analogies between them. In some sense, in fact, you can combine the two into one larger structure. So anyway, I call it the oscillator representation. And a comment here is that, so physicists and quantum mechanics, people like to talk about wave-particle duality, that sometimes a particle behaves like a wave, sometimes it behaves like a particle. And in fact, one feature of the symplectic group is this very large symmetry group, and it totally mixes up position operators and momentum operators. Once you have the symmetries of the symplectic group, you can't tell what kind of an operator you are anymore. And anyway, physicists call this confusion wave-particle duality. So the symmetries of the Heisenberg group or the Heisenberg-Lie algebra are what contribute to this rather confusing physical phenomenon. Okay, so we've constructed this representation of the metaplectic group, and we might then ask, okay, so what have we got here? What have we got, a typical representation? And the answer is no. It is a very atypical representation. It's extremely special. And I'd like to spend a little time explaining in what way it's special. And I'm going to do this by talking about the idea of the rank of a representation. Okay, so the symplectic group has a subgroup P, which is sometimes called the Siegel parabolic, which has the following description. So the group P is a product of two factors. This M is a block diagonal group that looks like this. So A can be any n by n invertible matrices. So A runs through the GLN, the general linear group, and then the block down here is the transpose inverse of the block up here, and then the off-diagonal blocks are zero. So that's what the M looks like. And then the P consists of matrices that are block upper triangular, so it's just got identity operators. This is the n by n identity operator on the diagonals, 0 below, and then this piece above is a symmetric n by n matrix. So the symplectic group has this thing inside of it, and the group of upper triangular matrices is actually commutative. and it's essentially the additive group of the symmetric matrices. So if I multiply two of these matrices together, all I get is the matrix of the same form with the upper left corner just being the sum of those two matrices. So these upper triangular matrices are just acting like the additive group of the symmetric n by n matrices. In particular, it's commutative. And then in some sense, this is natural. That is to say that it's correct to think of these things as being the symmetric n by n matrices, because also the action of the diagonal group by conjugation on the upper triangular matrices just acts in the normal way that the invertible matrices like to act on symmetric matrices. So everything is perfect, and we should think of this group as the group of n by n symmetric group matrices, the additive group of those matrices. So the idea is we want to take a representation of the big symplectic group and restrict it down to this small, very, I'm going to say simple, well, I'll say simple-minded. It's not a simple group, it's an abelian group, but it's a simple-minded group. It just is additive, vector space kind of thing. And so we want to have to worry about representations of this abelian, of this vector space. And it's well known that the representations of an abelian group, of a commutative group, are all, irreducible ones are all one-dimensional, and they're called characters. So the characters for the symmetric matrices just look like this. They can be, again, they can be parametrized by another symmetric matrix. So you take your symmetric matrix X, and you multiply it by T, this auxiliary matrix here, and then you take the trace of that product and you multiply by 2 pi I, and okay, there I am normalizing, I should apologize, I guess. And then you exponentiate that. So, but you have to multiply at least by square root of minus 1 in order so that this will be have absolute value 1, so it will be a unitary number. Okay, so these are the characters, the unitary characters of this group of upper triangular matrices. And of course, when you're talking about matrices, the first thing you want to know about them is their rank. So we have we have these characters of the group which are parametrized by these matrices. So we'll call the rank of the character whatever the rank of that parametrizing matrix is. And then, then if I have a representation of the symplectic group, I want to restrict it to this subgroup of symmetric matrices, and then I'll look at all the characters that appear in that restriction, and the largest rank of any character that appears, I'll call that the rank of the representation. So roughly speaking, you know, if you have something of small rank, it should be kind of a small representation. And if you have something of large rank, it probably is a larger representation. And it's actually not even clear that this invariant is, it's not a priori clear that this rank is interesting at all. It could be that the restriction of every representation of the symplectic group, being such a big group, to this little tiny group, it just sort of contains all possible characters of the group U, and so you wouldn't get any information at all by doing this. But of course, I wouldn't be talking to you if that was the case. So before going on, let me make a small refinement, which is that I've been speaking of the oscillator representation, but in fact, there are a couple different ones. So remember that there was this caveat in the Stone-von Neumann theorem that you had to fix the character on the center. And if you take different characters of the center, you can get different oscillator representations. Not very different, it turns out. It turns out that there's one for every one-dimensional inner product. So what are the one-dimensional inner products in over the real numbers. There's x goes to x squared, and there's x goes to minus x squared. So there's 2. There are 2, actually, oscillator representations in this situation. Yeah, so we need to fix the character, and the dependence of things are weak. So it turns out there's just 2 oscillator representations, one for positive oriented characters and one for negative oriented characters. And basically they're the same. It turns out that there's a slightly larger group of symmetries that switches the 2 oscillator representations. So anyway, there happen to be 2 of them, but it's, they look very much like each other. And okay, so then this is what says that the oscillator representation is really, really special. First of all, it has rank 1. It's as small as it could be and not be nothing, right? I mean, although that subgroup, the upper triangular symmetric matrices is very small, if you conjugate it around, it will generate the whole symplectic group. So if you just represented it by 1, by the identity operator, you moved it around, everything in the symplectic group would have to be represented by the identity operator. You'd have the trivial representation. So you can't have rank 0. So rank 1 is the smallest you can have, and the oscillator representation has rank 1. And an interesting thing about that representation is although the Heisenberg group is acting irreducibly, and the oscillator and the symplectic group is much larger than the Heisenberg group, actually it's not an irreducible representation of the metaplectic group. It has 2 irreducible components, and it turns out that any rank 1 irreducible representation is equivalent to a component of the oscillator representation. So there are just 4 irreducible rank 1 representations, and here they all are. That's of the metaplectic group, the 2-fold cover. So, so far I've been taking all your time to talk about a very, very special representation of the Heisenberg group, and then this very, very special representation of the symplectic group, or actually the metaplectic group. So what's the point of all this? Well, it turns out that that this very special object actually has a lot to say about representation theory in general, and it was this, essentially this is the representation theoretic aspect of the theory of theta series, which started in the early 19th century with Jacobi and was finally connected with the representation theory by André Weil. So here's the idea that we'll take the oscillator representation of a really big symplectic group and we'll restrict it to certain subgroups. And it's kind of you have to be careful about this, very careful about this, because typically, I mean, if you study representation theory, if you take a big group and you restrict take a representation of it, restrict it to a small group, usually the restriction is a mess. So how are you going to figure out what it looks like? And one thing we can use for a guide is the heuristic that if you know some operators that commute with something, you can learn something about the operator you're interested in. So in particular, I mean, a principle of spectral theory, ordinary commutative spectral theory, if you have 2 operators that commute, then you take an eigenspace of one of them, that will be invariant by the other operators. So if you know the eigenspaces for B, you can reduce the problem of finding all the eigenspaces for A to do it one eigenspace of B at a time. So, so this suggests that maybe we should look for things inside the symplectic group that commute with each other. So you start with some subgroup A, and then you look at the subgroup A prime of everything that commutes with it. So it's called the centralizer of A. And so you'd like to use A prime to help decompose representation of A. And well, if you want to do that, then it would be nice to have A be as large as possible, subject to having this group as commutator. So that means that A should be equal to A double prime, the full subgroup that commutes with A prime. And then it turns out that that the stops after that, and then if you consider A triple prime, the full set of things that commute with A double prime, then that's just A prime again. So that A and A prime then are each the full centralizer of each other in the symplectic in SPW, and this, we call this a dual pair. Okay, so we want to take the oscillator representation and of the symplectic group or the metaplectic group and restrict it to dual pairs and see what we get. And before I go on, let's mention that dual pairs are very special structures. There's only a few of them, and they've been totally classified. But any classical group will appear in a dual pair for some dimension of symplectic group. Okay, so here are examples. So a pair of general linear groups occur with each other as centralizer of each other inside the symplectic group of dimension twice the product of n and m. A symplectic group and an orthogonal group appear as centralizer of each other inside the symplectic group, again, of twice the product of the dimensions. And then these examples are valid over any field. I've been pretending I'm only talking to you about the real field, but really we want to talk about p-adic fields and finite fields. But over the real field also, a pair of unitary groups you can find can appear in a dual pair. So essentially all classical groups you can find somewhere in these dual pairs. And so here's an example of the kind of theorem that you can prove using the idea of rank and dual pairs. So you take, let me let OR be an orthogonal group. And again, this could be any orthogonal group, not necessarily positive definite. So this could be OPQ, where P and Q add up to R. And then if R is less than or equal to N, and I look at the restriction of the oscillator representation to that dual pair, it turns out that for every irreducible, and here I'm using these admissible representations again, you get a corresponding irreducible admissible representation of the symplectic group of rank R. And that this mapping gives you an injection then of the admissible dual of this orthogonal group into the admissible dual of the symplectic group of this particular sort of rank R guys. It's also known in this case that, so if you're really interested in unitaries, only in unitary representations, it's known that unitaries go to unitaries. And this was proved by me in one special case and by Jensu Lee of HKUST in the general case. And this was actually quite a few years ago. The unitary situation was actually understood before the admissible situation. So this just says, again, the admissible representations are a natural class of representations containing the unitary representations, and they've been the main things that have been studied by representation theorists in this context. And the unitary version was known about 40 years ago, but the admissible result is actually new. And also, actually, what I'm happiest about, although this is all pretended to be about the real numbers, what I'm happiest about is that this result applies also to finite fields. And before this, no result was known in the case of finite fields. Okay, so, and this correspondence is closely related to something that's been known in the literature as the theta correspondence, sort of the representation theoretic version of the theory of theta series. And this has also been an intensive subject of study over the past 40 years and has recently been more or less completely resolved. But this correspondence is somewhat different from the theta correspondence, although they're closely related. And let me finish with some examples of dual pairs that are intimately related with well-known physical systems. The study of n-harmonic oscillators is described by the dual pair UN, U1, unitary group, and definite unitary group in n dimensions, definite one-dimensional unitary group. And that's why I call this the oscillator representation. The theory of spherical harmonics, which is a mainstay of classical analysis, is more or less equal to the study of the dual pair orthogonal group in R dimensions and SL2. And then the space of states of an electron in a hydrogen atom supports an irreducible representation of the group O42, which is more or less the same as the group SU22. And Neumann here in the math department has shown that this representation appears in the dual pair of U22 with U1. And he's shown also that the other representations that appear in this dual pair are associated with slightly more general dynamical systems that involve magnetic as well as electrical attraction. Okay, so if I can summarize what I've tried to say is that you start with the uncertainty relations or the canonical commutation relations. This, when you look at the mathematical structure that lies behind them, you find this Heisenberg-Lie algebra and associated Heisenberg group. And then you have the Stone-von Neumann theorem implying essential uniqueness of this representation of the Heisenberg group. This, in turn, because of the large symmetry group of the Heisenberg group, gives rise to the oscillator representation of the metaplectic group. And then by considering dual pairs, you get fairly large families of representations with natural correspondences between the representations associated to groups which look quite different from one another. And it's the concept of rank which allows you to make these connections. Okay.
This concept of rank extended straightforward to the admissible case?
So, yeah, that's a good question. The answer is, what you mean depends on what you mean by straightforward, but you can extend it to that. Yeah, you have to. Of course, for finite fields, there's no problem. For a local field, you have to consider the representation of the unipotent group of the abelian group, and you have to do harmonic analysis, and you have to say that a representation has rank k if you look at the smooth functions in the group algebra, and the ones that have Fourier transforms whose support is disjoint from the rank k matrices if they get represented by 0. So there is a way of interpreting rank k in terms of local fields. Yeah.
So in the title you have uncertainty. So uncertainty has to be reflected after you apply Fourier transform, or?
I mean, for me, uncertainty was just. I mean, I've always thought of, as I said at the beginning, I've always thought of it as the Heisenberg canonical commutation relations, and I thought of uncertainty as the important physical consequence of the canonical commutation relations. But I've just been dealing with the mathematics of the canonical commutation relations.
Regarding the physics question, or maybe it was a physics question that was asked during the talk.
Yeah.
One of the fascinating things about quantum mechanics is how phases both don't matter from one point of view. From the other point of view, they're like the most essential essential thing of all.
Yeah, I mean here, I mean in constructing the oscillator representation, right? I mean you had to worry about exactly about the phases of the operators coming from the metaplectic group, and it's actually a pretty involved calculation to show that you can reduce them to just plus minus one, and it's also, you know, also an important technical point that you can't reduce them any further. That the plus and minus one you can't get rid of. And even like in the Heisenberg group itself, right? It's the center which is acting by changes of phase, and in some sense that doesn't matter. But on the other hand, it's it's those changes of phase which is making the whole action irreducible. So you're right. It really is. Really would like to hear from the physicists about.
Well, I can pretend to be a physicist.
Okay.
So one thing you can say is that if I take, say, a particle like an electron or even a person, and if I could multiply their phase by some unit complex number, that would have no observable effect on them at all. There'd be no way to tell that you've done that. But if you took that particle or that person and you sent them through a diffraction grating and split them, which is much easier for a small particle than for a person. So it goes around, moves in both paths. And then you multiply one of those copies by a phase, and then you recombine them. Then you can tell what phase has been accomplished by the interference patterns. So it's sort of only one phase of something relative to another when you add them, you detect the phase. But that's nonetheless somehow what makes the phases so important. But yeah, it's a very slippery concept that I've spent many years trying to understand. Because half the time physicists say that phases don't matter, and then other half the time they seem to matter.
Yeah, there are clearly situations where they matter quite a bit. But yeah, I'm not competent to tell you what the difference is.
I'll add a remark that, so Roger mentioned automorphic forms and theta series, but he didn't get into it. One very exciting thing that happened last year was done by a female mathematician whose name slips my mind, but she used automorphic forms to show the densest packing in 8 dimensions from the so-called Leech lattice. This was considered something on the order of what Ramanujan might think of.
Actually, in 8 dimensions, it's the E8 lattice, and in 24
dimensions. Sorry, the E8 lattice.
Yeah, right, and that was done with automorphic forms.
Okay, let's thank Roger.